As Wojciech said before, I joined the project as a student of the then master studies. Now I graduated. I have wrote my thesis about the couplet wind and fire scenarios based on the project that we did. And today I will present to you why we went with the open car park as a case study of ours. The first thing that is very, very good about it, well, not really good, but what is really motivational is that it is very, very burdensome in recent years. There is a lot of car park fires happening. They are happening every year, and they are having a huge, they are making a huge losses in case of cars, of buildings, and we are not really taking our lessons from one that happened in back and changing the things that how we are doing them. And also the open car parks are only ventilated with a passive system, with a natural ventilation that is fully driven by a wind. And for example, if there is no wind, there is no ventilation. And if the wind isn't blowing perpendicular to the open walls of the open car park, there is also no ventilation because there is no way that the air can actually get into the car park and take the smoke out with it. And talking about the burdensome of those fires, here I have prepared some examples for you. For example, there is a 2017 fire in England. The King's Dock car park have burned down, and it took 1,150 cars with it. The year after it, in New York, King's Plaza Shopping Center car park also burned down, took 120 cars with it. Also, a year later, the Douglas Shopping Center in Ireland also burned, and the 60 cars burned with it. Then another year later, we have the Stavanger airport car park with 300 cars burned, and the building basically collapsed on its own. So as you can see, they are happening every year. And now, last autumn, we have the Luton Airport car park fire in England. That was the biggest car park fire ever, with 1,500 cars burned and the building basically being unusable. And we in Poland also have a lot of open car parks. For example, here we have the car parks that I built next to the metro stations, so people can take their cars, park them, and then go to a metro and travel the city this way. And there is a lot of these car parks in Warsaw, and I will talk about them later. But now I want to tell you something about the requirements for the natural ventilation of these open car parks. In Poland, we have regulations that is saying that the surface area of the vents must be at least 35% of the surface area of the wall on each level, and that the distance between the walls with the openings must be maximum of 100 meters. So, for example, if we take a car park that is 50 by 20 meters, so its circus is 140 meters, and we take that the height of the car park is 2.7 meters, we came up with a wall area of 378 meters squared. Now we are taking the 35% of this, and we get 133 meters squared of required surface area of the ventilation openings. So we can spread them evenly, so we get 66.5 meters squared of the vent openings on each wall. And as long as we don't make the walls be like 100 meters away of each other, then it's good. And we have achieved the regulations that we need to pass. The second most The second most known regulations are from the approved document B from the UK. And they are quite different because they are not talking about the wall surface area, they are talking about the surface area of the level itself. So we have to provide the vent opening area equal or bigger than 5% of the level floor area. And we need to provide at least 1.25% of the floor surface area on each two opposing walls spread equally. So we can take now two different routes with these requirements. The first one is that we have the same car park, 50 by 20. So we have 1,000 meters squared car park. 5% of this is 50 meters squared, and we are taking it on two opposing walls, 25 meters each. And we are meeting the requirements. The other way that we can do it is we take 12.5 meters squared on one wall, 12.5 meters squared on the opposing wall. So we have the second criteria met. And now we can add the last 25 meters on the third wall, making that we have more access point of the wind actually to the building. So now we have only just one closed wall instead of two closed walls. And now that we know how the natural ventilation of car parks work, we will get to the project itself. And as Wojciech told earlier, we are working on the risk analysis of these car parks. And when you are talking about risk, you are talking about the probability of an event and the consequences of it. So I will talk you through the probability part of it, and then my colleagues will talk you through the consequences part of our risk analysis. For the probability, to calculate the probability of fire, we need to have some data that we can base it on. So we went for the data about how many cars there was in the years 2017, 2019 in Warsaw. Because we are basing the garage in Warsaw, so we went with the data that we have in Warsaw as well. And we came out that the average of the 3 years was 1,329,000 cars registered in Warsaw. Then we went with the number of fires of the passenger cars that were in Warsaw in those years. And we came up with the average of 319 fires per year, or 0.875 fires per day. With those data, we can calculate how likely it is that a single car will catch a fire. Now, when we take the filling of our park and ride car parks in the Warsaw, there was 16 of them at the time of the project, and we take the average number of parking spots in each of the car park and the data about how filled they were on a certain hours in a day, certain points. Like this, we have a data that shows us how filled the car park was at 6, at 10, at 13, and at 20. And we have it in percentages and with the number of cars that were expected to be in the car parks at these hours. We have the separate data for work days, for Saturdays and Sundays and holidays. And when we combine all of it together, the number of cars, number of fires, and number of available spaces and expected number of cars in the spaces, we came up with the probability of fire occurring based on the single vehicle that is entering a car park. So we have the probability per visit, and with the probability of a fire occurring in a car park with current filling state. And with this, we have met the probability part of the risk analysis. Now we will go to the consequences, to have the consequences made by the simulations, we have to think about the fire that we will be simulating. And the first thing that we need to know is how big the fire should be. What will be the fire that will be very good representing how the fires go with the car, how the car fires go. So we collect a lot of data from over 20 reports and different journals and publications. The data were ranging from a year 1991 to year 2022. So we have the new data, we have old data, and we have put them together to make one big database of the basically all car fire tests that there were ever made. In total, we have went over 70 research experiments that were analyzed to gather a data that we will be presenting to you. And from the experiments, we have gathered the data about the type of the propulsion, the vehicle masses, the peak heat release rate, time to peak heat release rate, total heat released, mass loss, and the origin of fire. By the origin of fire, I mean the place that the fire was first set in the experiment. And there is a lot of data that we have collected. So we need to make some kind of organization of the data to be able to analyze it and to be able to make a work with it. So we came up with the idea of grouping it through a mass, through a type of propulsion, and through origin of fire. So we have the small cars that the gross vehicle weight is up to 1,399 kilos. We have the medium cars, we have the big cars, and the very big cars, and they all have are ranging in different weight classes. And now we have the type of propulsion. We have the internal combustion engine vehicles, we have the battery electric vehicles, and we have plug-in hybrid vehicles, plug-in hybrid electric vehicles. And we have the origin of fires. It is under vehicle, cabin, body, and engine compartment. By under vehicle, we mean everything like burners, etc., put under the vehicle that were setting the car on fire. By the cabin, we mean the passenger compartment and everything that was burned inside. Body is everything that was outside of the car. And the engine compartment is everything that was in the engine compartment, like electrical circuit fire, like filters and things like this. And then when we group this data in this way, we could make some correlation between the variables that we have. And we made a separate study about this. And we were really, really shocked when we looked at the last graph that is presented here, that the method with burning the car from under it is really has a really fast time to peak heat release rate compared to other methods. So probably the method when you are putting like a burner beneath the petrol tank or beneath the electric battery of a vehicle, they can change how the fire is growing and the way that the vehicle is burning. And we want to also deeper into this data and try to make a lot of more information out of it, so we can come up with maybe a better understanding of what is happening during these tests. And another part is that we have to have some heat release rates from for our simulation. So we have grouped the data, and now we have a lot of data in our base, and we went with 5th percentile of the result of the small cars, which is 1.4 megawatts. We have went with 15th percentile of result of the small cars, which is 4 megawatts. We have went with 68th percentile of result for small cars, so we have 4.6 megawatts. We went with 15th percentile of results of medium cars. We have 6 megawatts there. We have with 19 percentile of results for big cars, we have 8 megawatts here, and with the 95 percentile of results for a small car, and we have 8.8 megawatts here. The 4 megawatts and the 8 megawatts mark are also known and are commonly used as the design fires for one vehicle when we talk about the 4 megawatts, and for 2 vehicles when we talk about the 8 megawatts fires. So now that we know the probability and we know how big the fires we want to have in our simulations, we need to put them somewhere in our model. So we have decided that the best location to put the fire will be the 4th floor of the car park, because the floor is most exposed to the wind effect, because it's above the buildings near it, so the wind can easily get to this level. And when we were placing the fire on the parking spot on the level, we have decided that the best position would be to put it in the worst possible place. So we have put it on the spot that is next to the entrance to the stairwell, that serves as a primary evacuation route for people, and also a primary access point for firefighters to go and put out the fire. So we now have the probability of fires, we now have the designed fires that we want to use, and we now have the scenario that we want to put them in. And I will leave you with this, and now Dr. Grzegorz Krajewski will tell you about the evacuation from the garage and other elements that we used in the assessment.